All right, here we go. Unit 4, Lesson 6. We're going to be talking about functions, their first derivatives, and for the first time in real depth, the second derivative of a function. The second derivative of a function is just the first derivative of the first derivative. And it's going to tell us a lot of things about our original function, just like the regular first derivative does. We're going to learn how to analyze those today. So let's say we have this function. F of x is, and I'll underline it in red because that's how the graph will be later, f of x is x to the fourth minus 4x cubed. So I'm going to breeze through this next part because this is something we've done before, just a quick refresher. Something we learned how to do was to take the first derivative of this function using the power rule, 4x cubed minus 12x squared. And we learned to analyze this function by first putting it in a nice factorable form. So 4x squared times x minus 3. That tells us a few things right off the bat. Number one, it tells us we have critical points or places where our first derivative is equal to 0 at x equals 3 and at x equals 0, right? Because if I plugged either of those in, the first derivative would be 0. And so we're thinking, okay, those are places where my function, where the slope of the tangent line is flat. So I'm going to have two places where the slopes of my tangent lines are flat. But there's more we have to do because maybe those are maxes and mins. Maybe they're neither maxes nor mins. Maybe they're like these saddle point looking things, right? So we had to make a sign chart to analyze it. And I'm just doing this as a quick refresher because we'll do sign charts with second derivatives too. But here we go real quick. We'd do a sign chart and we'd think about, okay, I know at 0 and at 3, I know two things. I know that the first derivative of x is 0 and 0. Right? So I know that my function, whatever it ends up looking like, right, my original function is going to have horizontal tangent lines at those two places. And I just need to fill in a little bit more info. So let's pretend we plug in something to the left of 0. If I plug in something to the left of 0, so like -1. If I plug in -1, okay, 4x squared, well, that's just 4 times -1 squared, that's 4, so that's a positive times -1 minus 3, that's a negative. So positive times a negative, my first derivative will be negative. So my original function must be decreasing on the way to this horizontal tangent line. Now let's think about, say, 1. If I plug in 1, I'd have a positive times, again, a negative. And again, when I'm doing that, I'm thinking of these here, positive times negative. That's what I'm doing here. So we'd have, again, a negative. So we have a saddle point in our original function because the first derivative, the slope of the tangent line, goes from negative to 0 back to negative. Kind of running out of room here, so let's just I'll back this up. And so right, negative, we just need to figure out what happens at x equals 3. So at x equals 3, let me just back this up a little bit. So negative, but let's say it's like really shallow negative all the way to 3. The question is this another saddle point or is this actually going to be a minimum? And so we think about, okay, if we plug in 4, if we plug in 4, we would have a positive times 4 minus 3, another positive. Okay, there we go. So my original function must go back to increasing. And so our two critical points here, they ended up being a minimum and what we would call a saddle point. And we can see that a lot more clearly here with the actual graph of this function, right? So we learned things like if your first derivative is negative, first derivative is negative, negative, it's 0, but then negative. The first derivative is negative, is below 0 all the way until we get to 3. And notice likewise, your original function is decreasing. At best it's flat, but then it's decreasing all the way till we get to x equals 3. At x equals 3, the first derivative finally becomes positive, and same thing with your original function finally switches to increasing. So sorry if that wasn't clear here. This is your f. This is your f prime. So we learned how to do that with a graph or with the function analytically. We're going to do the same thing, but we're going to talk about the second derivative, right? So we're going to have a third graph on this page. We're going to have a third graph for the second derivative, right? But all the second derivative is the derivative of the first derivative. So what we're going to use to analyze it, the second derivative is going to tell me things about the first derivative, which will then tell me things about the original function. It's just going to take another step of thinking, all right? So let's take a look at what this looks like. Like I said, the first derivative we know tells us when our original function is increasing, that's the first derivative is positive, decreasing, first derivative is negative, relative max or relative min. So either the first derivative goes positive to negative, right? First derivative goes positive to negative, if you think about the slopes of those tangent lines, or goes first derivative negative to positive, mins and maxes. The second derivative is going to tell us when our original function, and we're going to redefine these terms to make sure we know them, is concave up, concave down, or has a point of inflection. All a point of inflection means is switches concavity. And so let's see why this is. This happens, and it's pretty logical once you understand the following. The second derivative is just the first derivative of the first derivative. So if we just think through it step by step, we can see why the second derivative tells us about concavity. So let's start here. Let's start with this. When the second derivative, right, so just make sure you see here, this is the second, this is the first, and this is the original function, right? If the second derivative is greater than 0. So important here. The second derivative is just the derivative of the first derivative. So the second derivative being greater than 0 tells us that the first derivative is increasing, right? If something has a derivative that's greater than 0, it itself is increasing, and the second derivative is just the derivative of the first derivative. So if the second is greater than 0, the first is increasing. And I want you to think about what increasing means, right? If the first derivative is increasing, one of two things is happening to my original function. Either it is becoming less negative, right? I want you to see why that happens. First derivative, big negative slope. Less negative, but still negative, approaching 0. So your slopes are increasing. They're becoming less negative, or they're becoming more positive. That's the more intuitive side. They're becoming more positive from 0 to maybe 1 to 2 to 3. So notice the chain of logic here. The chain of logic, again, one more time. If the second derivative is greater than 0, the first derivative is increasing, and if the first derivative is increasing, the original function is concave up, like a smiley face or a cup. Versus, if the second derivative is less than 0, that means your first derivative must be decreasing. That means one of two things is happening. Either, and we'll go intuitive and then non-intuitive, either, this is the one that makes sense to people, either you're becoming less positive, right? Think about these slopes. High positive slope, decreasing slope, decreasing slope, decreasing slope. Notice I'm not saying negative slope, I'm saying decreasing slope. The slope is getting smaller, so say it's like a slope of 4, then 3, then 2, then 1. And now, this is the one that's tricky for people to imagine. Now my slopes are decreasing because they're getting more negative. It's like -1. That's like 0. -2, -3. So that is what we call concave down, like a frown. You can't really draw it ends up going into the smiley face, but you get it, concave down like a frown. And all an inflection point is, right? An inflection point is going to happen when the second derivative is 0. And all this means is that you're going from one kind of concavity to another. So if your second derivative goes from positive to negative, well, then you went from a cup to a frown. If your second derivative goes from negative to positive, well, then you went from a frown to a cup. And it's exactly at that turning point. These are what we call inflection points. These are what we call points of inflection. It's when the second derivative is 0, so you're neither concave up nor concave down. And so if I were to say second derivatives here, second derivatives go positive, 0, negative, or negative, 0, positive. Concave up to concave down, or concave down to concave up. Woo! So a lot going on there, but let's see all of these at the same time, right? So here's all three functions lined up. Let's just pick like one section to really analyze. Let's look at the section before x equals 0. So if we look at this here, right? Let's look at the three things that are happening here. My original function is decreasing, but if I think about what's happening, if I were to like just pick a couple of these, let's say this is like a negative 10 slope, and this is like a negative 4 slope. And eventually it's just getting like negative 1 slope. It's getting closer and closer to 0. So notice the two things that we could have figured that out by. Number one, my first derivative, right? So sorry, I should label these again. This is f prime. In red, we have f, and in green, we have f double prime. Notice my second derivative, or my first derivative, is negative, but increasing, right? So negative first derivative, but it's increasing. It's getting closer and closer to 0, just like my original function slope is getting closer to 0. My second derivative is positive. My second derivative is greater than 0 because my first derivative is increasing. And because my first derivative is increasing, my original function is concave up. And all of these same things that you can see from this graph could be done with our form of analysis, right? F prime of x you'd find to be 4x cubed minus 12x squared. You could do the same critical points analysis, but then you could also find the second derivative, right? 12x squared minus 24x. And so you could like factor out a 12x. You could have this is equal to 12x times x minus 2, right? And you would find inflection points at x equals 0 and at x equals 2. Inflection point, and that's the one, in this case, an inflection point is a critical point because it's a saddle point, but the one that you want to really make sure you see here is this second inflection point at x equals 2. So this is a point of inflection, and check out why, because my original function goes from concave down like a frown, concave up like a cup, right there. And that's the same place where my first derivative goes from decreasing to increasing. So it's a point of inflection. It's also a minimum of f prime. You can probably tell we're going to spend a lot of time on this. There's so much going on. It's a minimum of f prime, and it's where the second derivative switches signs. All right, so those three things all happen at the same time. The second derivative switches signs. The first derivative has a minimum because it switches from decreasing to increasing. And my original function has a point of inflection. All three of those things happen at the same time. All right, one last thing here, and that's going to be what we call, this one's going to be a bit of a break here. This one's called the second derivative test. This is just a really quick way to analyze whether a function has a local maximum, a local minimum, or a saddle point. And so what I want you to see here is that say we find find 4 critical points. So f prime equals 0, f prime equals 0, and we're trying to tell really quickly, like without even making a sign chart, were those minimums or were those maximums? And the trick here is to realize that if you know you have a horizontal tangent line, all you have to do is plug into the second derivative. If your second derivative is concave up, sorry, this is concave down, then you must be at the top of a frown or a maximum. If your second derivative is concave up like a cup, you must be at the bottom of the cup. You must be at a minimum. If your second derivative equals 0, you're at neither. You're at a saddle point. So let's check this out here. Second derivative test to find and identify all of the relative extrema. So if we do first, we find the first derivative is 4x cubed minus 12x squared. We find those critical values. This is 4x squared times x minus 3. So we find, yes, there are those critical points at 0 and 3, but again, this is like you're doing it blind. Critical points at 0 and 3. But say you didn't have this, and I asked you, okay, yes, you know it's a critical point. Is it a minimum or a maximum? You could make a whole sign chart, but here's a fun shortcut. Instead of making a sign chart, you can just say, okay, the second derivative is 12x squared minus 24x. Well, if I plug in 0, f double prime of 0 equals 0. So this is neither. This is going to be a saddle point. This is neither a max nor a min. It's what we call a saddle point. But if I plug in 3, I'll have to actually think about this one for a second. This is 12 times 3 squared minus 24 times 3. So that's 12 times 9 minus 24 times 9. What we're going to have here is a second derivative. Could make sure of this, but so we're going to have like what? 108 minus, who cares? It's something bigger than 108. So it's like 180, 216 or something like that. Either way, you're going to have f double prime, the second derivative of 3 is less than 0. What that tells us is it tells us, remember, we know that at x equals 3, we have a horizontal tangent line. What the second derivative just told us is that our function is concave up at that point, so we must have a minimum because the second derivative at 3 is less than 0, and we can see that here.